going to talk about the determination of relative density of a given liquid using the following items. 1. The Ritter stand and clamp. 2. The spring balance. And this spring balance is normally used for measurement of weight, though some are calibrated in grams, but you convert. And another, masses. These are the masses. Then we have the liquid labeled L. We have the water labeled W. It's assumed we don't know the value of this. This is just the liquid L. Liquid L. We want to determine the actual value of this particular content by relative density. We'll compare this to that of water using measuring scales. So look at this. Anytime you want to make use of the instruments, first you check the zero error. If the zero error is not in order, you work on it until it is at zero error. The zero error. You must correct the zero error of the instrument before you make use of it. That's one. You can't just pick an instrument and start using it. So this is the zero error now. It is exactly a zero. The same thing with this one hanging. This is exactly a zero. The one I want to use is at 0. It's corrected. So I want to make use of this. The spring balance. Now, for this spring balance, I have the masses. The first mass here is 50 grams. So I'll simply go to the observation. This is the table. So for me to go into this, first, I'll look at this particular diagram. What's the content here? The Ritter stand, the clamp, the what? The spring balance, and then hanging mass. So from this now, first, we talk about the mass given in grams. This mass now will be converted to the weight, W1, which will be in Newton. And when the mass is converted to weight, we now proceed with the weight in order to obtain this particular weight now in water as W2 Newton. So this one now, water, inside water. When this weight is inside water, this is in air, A-I-R, air. This is the W3 in Newton when it is in liquid L. Liquid L. Then after this, for you to proceed, you must know the difference between, or the upthrust between air, the upthrust of this particular weight in water, the upthrust in liquid. So you come back and say that you can name this U equals W1 minus W1 minus W2. So this is called upthrust, measured in Newton. This is the upthrust in water. U in water. In water. Then you can also move on to the upthrust in liquid by obtaining the value of V or X or Y. We can change this V, X, Y, or anything. We can make this one now, we can change it to X. Change this one to Y. Any of them. This is still upthrust. This is still upthrust. So for this one now, it is W1 minus W3, also in Newton. And this is now upthrust in liquid. Upthrust in liquid. Upthrust in liquid. So for us to complete this table, we have a serial number. This serial number IV, and the V. We can place 5 masses. We can place more than 5 masses. We can place 4 masses just to obtain the complete table. So this is the observation table. And we want to observe exactly, for us to determine what is called, for us to determine exactly the upthrust in liquid and the upthrust in water. We first observe that of the weight in air. So from here, we can now get the table. So let us look at exactly the experiment. We are taking the first one as 50, second one 100, 150, 200, and 250. These are the masses required. So I want to use these masses. First is this, 50 grams. Second, 100 grams. When I combine these two, it will give me 150. I combine these two, 200, combine all to 250. So I'm using these 3 masses to achieve this goal. So with this now, I will weigh this in air. Weighing this in air, when the mass, this mass, hanging mass now is 50 grams. The scale converted these 50 grams to what is called Newton or weight. And look at it exactly. Weight is equivalent to mg, mass times acceleration due to gravity. When a value is in gram, for example 50 grams, you divide by 1000 to change to kilogram before you multiply by 10, and that will change it to weight. So all these in grams, I will change all of them. So this is how the scale changed 50 grams to weight. What is reading now is 050, meaning, let's find out from here. 50 divided by 1000 will give me 0.05. Multiply by 10 is equivalent to 0.50 Newton. So this is now weight. That 50 grams is now converted to weight. That's exactly what we observe from here. So looking at this now, this is 0.50. This mass now is converted to weight. That is 1. And as long as this mass is converted to weight, I can now proceed with the experiment. I'll move this. The first one is weight in air. Weight in air. Second one is weight in water. Yeah, W2, water. The weight when it is in water. So I'm going to take up the reading here. This one. So as I look at this now, I'll take up the water. This is water, W. Place the water under. Adjust this until it is completely dipped into the water without touching the walls of the beaker or the bottom of it. Then I can now take the reading. From here I can read 0.4. I can read 0.42. 0.42 in water. 0.42 in water. This is water. So after taking the reading, I can remove it from the water. Or I will simply adjust. Instead of pulling it out, I can keep the adjustment. So I can adjust again up and allow the water drops. Allow the water drops so that I will not transfer this liquid into the next one. I'm through with this one. I'll bring this. I can still clean up. Can use paper, touch this or rag just to remove the contents. I'll then place this under and then move again. This is the liquid L. We'll adjust again. Adjust again. So this is it. It's already completely immersed. I can now take the next reading here. Is 0.45. 0.45. 0.45. So this is 0.45. 0.45. With this now, I can complete. I say 0.50, which is W1, minus W2 to give me that of the difference in water. And what is it? And what is it? 0.50 minus 0.42 will give me what? 0.008. So here will be 0.080. This is evaluation. It must be 3 decimal places. And now look at this again. 0.50, that is W1, minus 0.45. 0.050. So this is upthrust in liquid, upthrust in water. Upthrust in liquid, upthrust in water. Upthrust in water, upthrust in liquid. So with this now, I will now move on to, I'll change to 100. So I can now remove this, remove 50. I can remove 50. And then check up the next mass. I simply open the loop. This is a loop. We use a form of loop so that I can return it without falling out during the experiments. So this is the loop. So I'll change the loop to 100 grams mass. This is 100. 1, 2, 3, 4. It's stable now. So this is This is another mass, and that is mass of 100. Mass of 100. So for mass of 100 suspended, it gave me, this one gave me 1.00, 1.00, 1.00, 1.00. That is the adjustment. 1.00. Then with this now, I can move the water under and adjust again. If you look at it, you see it is very, very free. Very, very free. Because if you allow it to rest on the wall of the container, it will not give you the actual reading. So this one now, this one now gave me 0. This is 0.86, 0.86, 0.86, 0.86. Then we'll adjust again out of water. So that we move to the liquid. We move to the liquid L. Move to the liquid L. This is 0.95. 0.95. And then let's find out the difference. The difference here, weight in air minus weight in water is what? 0.140. Weight in air minus weight in liquid L, 0.050. 0.050, 0.50 cannot be. Let us go back to it. That of, let's go back to it. Let's adjust this again, because there is no way you get the same reading. That is 0.97. 0.97. 0.97. So this is supposed to be what now? Zero point 0.030. That means the reading is not in order. The reading is not in order. So we must go back and find out exactly what happened because of the difference between the two. So let's find out exactly what happened. So let us now adjust this back to normal. Okay, it's not. The zero error changed. Okay. Okay, that means we'll repeat this. Sorry. This is 0.92. 0.92. So get me the result here. 0.080. I think it's correct now. I think it's better now. You know, sometimes one or two things may change the reading error of this, the accuracy. Okay. So for 100 now, completed, we move up to the next. What are we going to do now? We add 50. This is 50 grams. We add the 50 grams here to make this 150. So we have 150 now. This is 150. Let's change the so this is 150. And that 150 will give us what? The 150 will give us what? 1.50. 1.50. That's the reading. 1.5. That's 1.50. That's the reading. That is weight in air. 1.50. Then we now adjust for the reading in water. The reading in water. This is the reading in water. That is so this is 1.35, 1.35, 1.35, 1.35. We adjust. This is 1.41, 1.41, 1.41. Now get me the result here. W1 minus W2 is what? 0.150. 0.090. 0.090. Then we now move over to, we change to 200. For us to change to 200, we remove 50 and add 100. We have 200 now. This is 200. And this is reading 2.00. This is reading 2.00. 2.00. 2.00. 2.00. 2.00. We now move up to this. Adjust now. This is 1.74. 1.74. 1.74. Chemicals. This is liquid L. This liquid L. We can change this. It's already at 0 again. That means the reading so let us find out. This is also at 0. Let's see what will happen here. This can, as long as there are instruments, they may change their readings I need I'm adjust. Come adjust to go to this one first. Mara really. Mara ready. They say okay. Okay. Thank you. So this can also happen to anybody, even in exam. That's why you normally change instruments. That's why you normally change instrument to. That's why you normally change instruments. The moment you observe any error like that, please indicate. The whole thing not in line. But not that I say change here completely. So let's look at the whole thing. Let me verify before. Please get me what do you call it? This to wine. Don't worry. Let me continue. Let me add. Let me add another mass. The same mass with this. This is still 250 grams. Still 250 grams. Mm-hmm. 2.5 is still correct. 2.50 is still correct. Let's find out that of the water. It's still correct. This is this is 2.20 here. 2.20. Let's still repeat it. Let's adjust. Allow it again in, so that we'll be sure. .20. Okay. Okay. This is resting on the floor. It's floating. So this is 2.25. 2.25. Let's find out the difference and know if the whole thing is in order. What's the difference here? 0.300. What's the difference here? 0.250. Yes, the decrease is now in order. This is exactly the right thing. Sometimes it's not always easy using all these calibrated instruments. You repeat and repeat and repeat until you obtain good results. That is exactly. So with this now, we can now remove completely and talk about the determination of the relative density. So let's now talk about the determination of the relative density. Determination of the relative density. Determination of the relative density. I'm looking for meter rule. There was one meter rule I dropped here. I dropped here the other time. No, not transparent. That is long, that long wooden something. For me to take. It's not there. Okay. Okay, let's continue. Now, for us to determine the relative density, we're going to plot actual graph, but I will sketch the nature of the graph here on the board. You know that the board will not give you the complete results. You sketch a graph with 0, 0 origin, vertical 0, horizontal 0. You may be asked to plot the graph of W1 minus W3, which is Y. So Y in Newton. W1 minus W3, which is liquid, against X. And X in Newton is W1 minus W2. That is X in Newton. W1 minus W2. That is X in Newton. When you sketch this graph, as you look at the upthrust in water, ended 0.30. Upthrust in liquid ended 0.25. You can take up a scale. You can take up your scale from here of maybe 4 cm to 0.1. 4 cm to 0.1. So I can come up here. This is 2 cm, 0.1. 2 cm, 0.2. 2 again, 0.3. 2 to 0.4. Then on the horizontal, the same. 2 to 0.1. 2 to 0.2. 2 to 0.3. It's just a sketch. And 2 to 0.4. So for us to give you the idea of what to plot graphically, you use actual graph, a scaled graph, to plot the difference. The value of y, first value of y is 0.05. This is 0.1. Here is what? 0. What? 0.05. So this is the line 0.05 against the first value of 0. What? 0.08. 0.08. And you know from here that you have 10 lines. 10 lines. You have this 5, you have 10 lines in 10 lines here. So if I plot here 0.05 against 0.08, which is closer here, that is the meeting point. I'll circle it. That's the meeting point. I'll circle it. Then I'll come back to this 0.08 for the vertical against 0.14. 0.08 is somewhere here also against what? Against 1 point what? Against 0.1. This is 0.1 what? 15. So here should be 0.114. 0.14 against 0.14. You plot. Then 0.90 against 0.15. 0.90. 0.90, which is close to 0.1 against 0.15 against 0.15, which is exactly here. You plot. This is in line. You plot. I just want to show you exactly. You plot and then circle. Then 0.20 against 0.26. 0.220 here against 0.2526. You plot. 0.25 against 0.30. 0.25 against 0.30. You plot. You can see it is forming a straight line. Though the board has no scale, yet it's forming a straight line. And when you want to take your line, you place your ruler such that you determine the line of best fit. 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 Okay. So for me to run a straight line, I will apply what is called line of best fit. There is no way all the points will enter the line as long as physics is concerned. The principle is based on line of best fit. Some will be out to the right, some will be out to the left. That's exactly the principle. So for me, you know, this is, but this may not give me the exact, but this is a rough, this is the rough, this is the information, kind of information of what you're looking for. So here, if I place this across, I will look for the line of best fit. Line of best fit. I can take this place. I can take this place. I can take here. And take this line here. All right. So look at this now. This is what is called line of best fit. This point is completely out. This one is out this way. This is a point. This is a point out. But 1, 2, 3 almost entered. You know, this is rough. This is the line of best fit. I can now take my slope from here. I'll take the slope from any point, irrespective of the points. Slope is meant to pass through any point because the line passed through the major area of the best fit. So I can take up my triangle from any point. I can take my triangle, a big line, a big triangle. I can take a big triangle from here down. Can also take this from here down. So this is my slope. So this slope I have here, change in y, which is in Newton, change in x, which is in Newton. And then I'll take my reading. The board may not give me the exact information, but the actual graph will give you the right information. So from here, I will now take my reading. This one already. So I will write down here slope. Slope S equals change in y, which is in Newton, against change in x, which is in Newton. And you know that Newton will cancel Newton at the end of this, because what the slope will give you will be the information without units. Without units. So you come back here and read. So taking my reading from here, I'll simply take the reading directly from this point. The position here is 0.35. 0.35. The reading of this. So I have the slope as equivalent to 0.35 minus, I'll read the down one. This down one is 0.05 minus 0.05. All divided by, I'll read the horizontal. The horizontal here gave me 0. This place gave me 0.42. 0.42 minus this place gave me exactly, this is 0.05, maybe 0.07. 0.07. So I can now determine my slope. Please subtract this for me. 0.30 divided by what? 0.35, which will now give me, divide this for me. 0.857, that's 0.86. 0.86. It has no unit. 0.86. Now, what is the value of this 0.86? Now, because this is a sketch, and I got this. If I use a real graph, I will obtain a value between 0.80 and 0.84 and 0.84. The real value is between this. This is from this to this. This is the range of what I'm supposed to obtain. Because the liquid here is said to be kerosene. And kerosene has a relative density. Kerosene has a relative density. Kerosene, relative density of 0.83. That is kerosene. That's kerosene. That is kerosene. It has a relative density of 0.83. But due to the sketch, due to the free space on the board, I was able to obtain 0.86. 0.86. So this is exactly the proof. So looking at the whole information now, I was able to prove that the liquid labeled L is kerosene, though I got 0.86 instead of 0.84, 0.83, but because it was a free space on the board. So this is an experiment that proved that the relative density of this liquid can be determined. And that's exactly, anytime you carry out such experiments with kerosene, with paraffin, with red oil, and other values, you still get the relative density of that particular liquid. So I use the masses: deep in water, deep in liquid, deep in water, deep in liquid. The upthrust gave me the exact information. And that is exactly. So this is the proof, the evidence that this particular liquid labeled L, the liquid labeled L is kerosene. Now we can state the precautions. We can just look at the precautions taken. The precautions taken. One of the precautions for me to start the experiment, I took note of the zero error of this particular instrument. I took note of the zero error, or I corrected the zero error of the spring balance before the experiment. That is first precaution. That's first precaution. Are you with me now? Remember the statement. I did what? I corrected the zero error of the spring balance before the experiment. That's one. Secondly, I prevented the mass, the loaded mass, from touching the walls of the beaker during the experiment for reading accuracy. For reading accuracy. Because if you allow the beaker, if you allow the mass to rest the wall of the beaker, the reading will vary. The reading will change, which actually happened to us here during the experiment. Now, number three, I suspended the spring balance on a rigid support. So that it can be stable throughout the experiment. And finally now, I took the readings directly from the scale. Of the spring balance to avoid error due to parallax. I took the readings directly from the scale of the spring balance. To avoid error due to parallax. Which means if I view from above, I will not be able to get the actual reading. But if I take the reading directly where the point is, just like I did, I'll be able to note the reading directly, the exact information. So with the whole experiment, we're able to prove that the upthrust in liquid over upthrust in water is equivalent to the relative density of the liquid labeled L. So that L is equal to kerosene. Thank you very much.